Okay, so this is lecture 24, and today my plan is to continue discussing spontaneous symmetry breaking. So we introduced the idea of spontaneous symmetry breaking last time, and since it's such an important idea, we need to get familiar with it, and not just with the equations but also with the physical ideas behind it. And so I'll try to stress those ideas again. So let me remind you very briefly what we did last time. We considered first we considered the real case, but then we considered a complex scalar field and a Lagrangian for it, and we had a simple Lagrangian that actually in today's lecture I will prefer to write it as this. Yeah. So this has a constant term, then it has, if I expand out this, I get plus twice lambda phi star phi minus lambda phi star phi squared plus a constant. But the constant only plays the role of making the minimum of the potential at 0, which is a good thing. You can see that directly. The minimum is at phi star phi equals a squared, and the value of the potential is 0 there. That's very clear. Now, the sign of this, I call it a squared because I want to emphasize that it is a real positive number, but I could have just called it alpha, and I could have taken either sign. Whatever sign I take, the Lagrangian doesn't mind, because the Lagrangian is U1 invariant for both signs, and the Lagrangian is bounded below for both signs. So there's no bias in the Lagrangian to have one sign or other of this number a squared. Could be positive, could be negative. However, the fact is that, sorry, here there's an a squared. If a squared is negative, this is a conventional mass term, but if a squared is positive, then it's not. And the shape of the potential, which we'll draw as V of phi against phi 1 and phi 2, the real and imaginary parts of phi, the shape of the potential in the case when a squared is less than 0 is simply that. Remember that this thing is minus the potential. So the potential is minus this term plus that term. But if a squared is negative, then this also is plus. And so it's this kind of bowl-shaped object. Seeing the bowl-shaped object, you know that it is U1 invariant. The U1 invariance is the fact that this is a solid of revolution. It's the same as the fact that it depends on phi star phi. Okay, mathematically we say phi star phi dependence makes it U1 invariant because phase on this is cancelled by complex conjugate phase on that. But in a picture, it's simply having a potential which is shaped like a solid of revolution, and therefore revolution itself, which is the phase acting in the phi plane, is a symmetry. It's just obvious. Now if a squared is positive, it's still symmetric, still has the same, it's still a solid of revolution, but the shape of the solid is this. It's just a different shape. Okay, but it's still a solid of revolution. Just take this double well curve and rotate it about the vertical axis, and whatever you get is the potential. Now both are U1 invariant potentials, therefore both are U1 invariant theories, because the kinetic term anyway is always U1 invariant. But in this one, there's a single minimum, and so if I act on this minimum with U1, I don't get any new minimum. This is the same minimum. So it's just a single U1 invariant minimum. And here on the other hand, when I rotate this, I get a circle and this is a circle of minima. Related points on it are related to each other by u1. Because u1 rotates the whole figure, so it rotates any point on this circle to another point on the same circle. Okay, this is the situation where we say the symmetry is not spontaneously broken because there is a unique vacuum configuration, and here we say it's spontaneously broken because there's a space of minima which are all degenerate with each other, but any one of them is not invariant under u1. But the entire space of minima is invariant under u1. That is the key idea of spontaneously breaking a continuous symmetry. Yes?
I think we talked about this last time also, but I'm a little confused about it still. When we have two minimum, or in this case an entire degenerate circle of minima,
Yeah.
Whenever we are doing an amplitude,
Yes.
far past and far future minima, classical vacuum that are there, do we have to sum over all the
No, we pick a single minimum in the past, and we can pick a single minimum, and we pick a single minimum also in the future. And now, if those two are the same, then the simplest classical solution is that the minimum value is in the classical solution just takes the minimum value for all time. If we pick two different ones, then we must have a classical solution that starts in the one minimum and ends in the other, and we are going to do that next time. So we'll postpone the question till that's also what I said last time. We'll postpone that one to the next lecture. But and it's an interesting case. But even if I have the same minimum at minus and plus infinity of time, I could still have a non-trivial solution that goes from one. Goes somewhere and comes back to that minimum. That also will be discussed next time. So all such cases are simply, they are more complicated than the simplest case, which is to pick the same minimum in past and future. But the important thing is we have to pick one. We can't pick many all at the same time, and that is why spontaneous symmetry breaking actually takes place. And finally, this picture, although it's by no means the most general because there's just one complex scalar field, there are many more complicated theories and which we'll write today. But this simple picture gives away a basic fact, which is that the U1 symmetry relates all the minima. That means all of them have exactly the same energy. That means that if you are in the minimum, that means if you are on this circle of minima, then you don't experience any potential. The only way you will experience a potential is if you try to climb out of the circle of minima on this side or on that side. Then you will experience a potential. But if you just want to happily roam around on the circle of minima, you have no potential at all. And this is the essence of Goldstone's theorem. It actually says that there's a mode of the field, or there's a field in the theory, which experiences no potential at all whenever a symmetry is spontaneously broken, as in this case. In this case, the symmetry is not spontaneously broken and there is nowhere to go from here. So all the modes of the field actually climb up the potential. One mode, for example, phi1 climbs up this way and phi2 climbs up this way. But both of them climb up. There is no way where for them to go remaining at constant energy. So there is no massless particle in this case. But here, the radial coordinate climbs, the radial part of the field climbs up a potential, but the angular part doesn't feel a potential, and that's the Goldstone boson. Yes.
Say some of the derivatives are zero, but for the radial part is still not zero, right? So how do you?
Some of the derivatives of what?
So the potential is zero in a certain.
The potential is simply zero on the circle. Yes.
Right, but potential will be the rate of change. So, but it is not all the derivatives are zero, right? The potential is increasing in some.
So there are two linearly independent directions, right? It's a 2D potential, so it's only a 2D space. So I have to pick some basis of fields in that. This is a field space, so I have to pick a basis. Here I have picked phi1 and phi2. But in the calculation we did last time, we picked r and theta. So different basis for the same field. Okay, if I pick r and theta, so in fact that I'll show you now. If I pick r and theta, then r experiences a potential and theta strictly does not experience any potential, because by construction it is pointing along the circle of minima. Okay. However, if I pick phi 1 and phi 2, something different happens. So let's take a top view of this figure. So here is the circle of minima, and here is where I am, because I choose, I'm working in phi 1, phi 2 basis now, real and imaginary, and supposing I choose the vacuum expectation value or the classical solution to be phi 1 equals this A and phi 2 is 0. Now sorry, this is not the this is not correct. I'm doing the top view, so actually this is phi 2. Right? Okay, and V is out of the board. Okay, so now at this point, phi 2 points that way. Everywhere phi 2 is a vertical direction. So is phi 2 the Goldstone boson, yes or no? And here it's a little more subtle. What you'll actually find is that yes, phi 2 is a massless field, but phi 2 does have a potential of cubic and quartic order, and we are just going to show that. And the reason is that if you deviate more than lowest order from here, then the minimum is going that, the circle of minima is going that way, but phi 2 is still going this way. It's not the angle along the circle of minima. So therefore, phi 2 does have a potential, despite what I said about Goldstone's theorem. Okay, and I'll show you that just now. It's kind of a rerun of last time's calculation, but just done in a different basis. And it will illuminate little bit what is going on here. So give me a second to find it. Yes, good. So in this case, if I'm in the phi 1, phi 2 basis, then I expand the Lagrangian. So my classical solution I choose, phi 1 classical is A, that puts it in the minimum, if phi 2 classical is 0. Okay, and then the fluctuation, so phi is just written as A plus eta, phi is written as A plus eta, phi of x, A plus eta of x. So phi 1 is A plus eta 1. And phi 2 is just eta 2, because A is real. Okay, and I plug that into this Lagrangian. What do I get? Well, no big surprise. First, for the kinetic term, I get del mu eta star, del mu eta. Okay, so in this diagram, actually, these will be eta, because it's a coordinate which, this is the origin of my coordinates. So this is eta 2 and this is eta 1. Sorry, yeah. Yeah. Okay.
So the vectors on that point will be eta 1.
Sorry?
Like at that point they are eta 1 and eta 2, right?
At this point? No, they are everywhere. This direction, rightward is eta 1 and upward is eta 2.
But only at the fluctuation at phi 1 equal to A and phi 2 equal to 0 will be those. Only then those will be.
Yeah. But of course, once I have eta 1 and eta 2, nothing stops me letting them be large in the Lagrangian. And if they are too small, then I won't see any quartic or cubic terms. If they are large enough to see quartic and cubic terms, I'll see that those are not absent, they are present. And that will show us that this is not really, I mean, in some sense, most textbooks will call this also the Goldstone boson. All we are saying is it doesn't have all the properties of the Goldstone boson. It will be massless, but it won't be potential-less. While the true coordinate along the circle will be massless and actually potential-less, which is a stronger statement. It's axionic, to be very clear. So let's continue doing this. So this gives me this plus, I guess, lambda, 2 lambda a squared, and then phi star phi, which I write as a plus eta star, a plus eta, and then minus lambda, a plus eta star, a plus eta whole squared. apart from the constant term lambda a to the fourth, which I don't need to worry about. So also I'll drop this constant 2 lambda a squared a, which will cancel that constant term. Okay, now let's so as usual I'll choose a bit of normalization. So my eta will actually be 1 by root 2 of eta 1 plus I eta 2. So that eta 1 and I and eta 2 come out normalized, right? And I get del mu eta 1 squared, kinetic terms of both, that's what I certainly expect. What else do I get? Well, you'll find some linear terms, but they have to cancel, and you can check that they do cancel because A is the solution of the equation of motion. So that's not surprising. And constant terms we are dropping. And when you write the rest of it, you find that I get minus lambda a squared phi star phi, lambda a squared eta 2 squared plus order eta to the cubed. Eta to the cubed means it could be eta 1 cubed or eta 1 squared eta 2 or eta 2 squared eta 1 or eta 2 cubed, any cubic term or higher, and the only higher term will be quartic terms in eta 1 and eta 2. They are there, I'm just not writing them. Okay, now what happened? Well, I did something wrong. Eta 1 this is. So eta 1 has a mass. Again you see that the mass is not, okay, so let's see, yeah, the mass is not, so the mass in this thing was, okay, let me not try to compare. Anyway, the point is that this is the mu squared parameter we had last time, and that's the mass simply, okay. So it has a mass, and eta 2 doesn't have a mass. So this is, yes. Yeah. So this root 2 is here, and with this normalization, these came out correct. Last time the root 2 was put in front of R, the radial one. Both calculations are useful, by the way. Normally textbooks do this one. I like to do that one, but I should have perhaps done this one first and then that one. The order doesn't matter too much. They have different features. This is easier to do. You don't have to think through this radial and angular field. It's a bit weird. The biggest reason why this radial and angular field is weird is that decomposition only makes sense when you have a spontaneously broken symmetry. If I had an unbroken symmetry and I went to this r and theta variables, then theta wouldn't have a sensible kinetic term. We showed that last time. So it's like a special choice of coordinates only to study broken symmetry, while this choice, saying that there's a real and imaginary part, is natural to study any field theory. If it's a complex field, you can always write it in real and imaginary parts. So books do this. What books don't often do is comment on the meaning of this result. So they say, look, there's no eta 2 squared term. That is the key point. Okay, and why is that? If you trace through the calculation, which I would encourage you to do, what happens is when I multiply this with this, I get a cross term A times eta plus eta star. And what is eta plus eta star? That is proportional to eta 1. So eta 1 comes in that cross term, but eta 2 doesn't. Okay, eta 2 comes in the eta star eta term, of course, along with eta 1. So if it was only eta star eta, then we would have the same mass for eta 1 and eta 2. Because of this cross term, there's another contribution for eta 1 squared. Okay, and that's the one, I hope I said that right. It comes from here, sorry, I was pointing to the wrong place. So what happens here is you have a squared plus twice a eta plus eta star, which is eta 1, and this is inside a square. So you will get an eta 1 squared term from here, okay, in addition to the normal mass term which you get from here. So eta 1 and eta 2 actually have different contributions to their masses, and when you collect the contributions all carefully, you find that the one that survives is the mass of eta 1, and the one that should be the mass of eta 2 vanishes. So eta 2 is massless and it's a Goldstone boson. But these terms are easy to calculate, order eta cubed and eta fourth, and they're not zero. They're not zero for eta 2. though it's supposed to be the Goldstone boson. So this is the subtlety I wanted to emphasize. However, if you go over last time's calculation in terms of r and theta, then theta is really an axion. It absolutely doesn't have any potential, and that's the real full powerful statement of Goldstone's theorem. Yes.
So when we did the r theta splitting, we saw that theta did not have any potential.
Yeah.
Just a
Yeah.
axionic kind.
Yeah.
Whereas here there is some potential for the
Eta 2.
massless particle.
Yes, for the massless particle.
Now,
Absolutely.
if we calculate some scattering amplitudes or something,
Yeah.
We'll have to take those, like when we have that L interaction in the
Yeah.
numerator.
Yeah, of course, the
we'll
potential
have to
terms
do
are there.
some
Absolutely.
So when I observe a particle, a
Ah.
massless
Ah.
scalar particle, or the one with the mass,
Yeah.
since the masses in both these cases are consistent, like you have one
Yes.
massless and one with
Correct.
root
Yes.
2 times that.
Yes, yes.
But in one case, I would not have any perturbation terms for the massless
Correct.
scalar.
Correct.
Whereas for the other one, I
That's
would.
right.
So then, how do you?
It's a different basis for the fields.
Right, but
So-
physically observable stuff should be same.
Not
right?
really. It's one could argue it's not the same particle. In fact, the it's a good question, and I honestly haven't thought it through. But you can sort of see what's happening here, which is that so for example, if you supposing I took the vacuum expectation value not to be a but a times I. So along the imaginary, I could take it at any point on this circle, right? So I could take phi classical here. Now I find that eta 1 is massless because it is the tangent to this circle, and eta 2 is massive. You can do that calculation.
No, but my
So,
question is like you will still find a consistent masses in any case. Because
Correct.
You will
Yes.
get one massless and one
Yeah,
massive.
yeah.
But the potential that you will get will be different in each
No,
case.
I'm just saying that if I expanded around this, I would have a eta 1 and eta 2 are still the real and imaginary parts of my original field, right? But I would find one is massless and the other is massive, and the other, doing it the other way, I'd find the reverse. So you might worry that which of the ones is the experiment going to show. So the point is that there is one mode which is massless or which is Goldstone, and there's one another independent one which is not. And I can just choose to do my experiment with that mode, or I can do my experiment with something which is not exactly that mode, but it's still massless. Eta 2 is massless. So the only thing I'm not sure is why do we call eta 2 a Goldstone boson when it's not really the mode which goes around this. I think the main reason is that to quadratic order it's the same. So to quadratic order there's no potential for eta 2, and that's the statement, it's massless.
But
Same
to
as for
quadratic
theta.
order, if you take any tangential on any like theta,
Yeah,
and
yeah.
call them some eta 2 dash, then
Yeah.
to quadratic order, any tangential
Exactly,
field
exactly,
will be
exactly. And if I take all tangential, that is the theta
That is the
coordinate. Yeah, that's the idea. Let me think over your question about how experimentally I would know which particle I'm talking about. The usual statement is just that a massless particle arises in the spectrum, and all I'm really emphasizing for you is that it's not only a massless particle, it's really a mode that is rolling on a space of vacua, in this case a circle of vacua, freely with no potential. Nevertheless, it's interacting because remember last time theta had derivative interactions. So there was r del theta, that's a cubic term. So it scatters, it's not that it's a free particle. But it's constant, if you like, the constant part of it is non-interacting. That's what an axion actually is. And in fact, I can remove the constant part of an axion field by the axionic shift symmetry, exactly what we discussed long ago. So it all falls into place. Good. So this is the physics of this Goldstone boson. And then as I told you last time, and I won't do it again, we can do the r theta coordinates, and we can get a stronger result, which is that r has a mass which is the same as this mass, and theta not only has no mass, but it doesn't participate in any cubic or quartic interactions except through its derivative. Okay, so that's the summary of this model. And now if there are there any questions? Otherwise I'll move on to more general models.
So,
Yes.
just for clarification, Goldstone boson is one for which the potential is entirely zero.
Yes.
Not just the mass term.
Yes. But okay, I mean, in the rigorous proof of Goldstone's theorem, that's what we show. But people refer to this field eta 2 as the Goldstone boson, and it's not what you just said. It's massless, but it still has a potential. So, I mean,
So
there's a little bit arguing over words. Like different people use Goldstone boson loosely for any mode which is massless at the minimum, at the chosen minimum, or for that mode which is not only massless but propagates around the circle of minima, which is a more special thing. It may not in practice be easy to find that mode which propagates along the circle of minima. For example, if the space of minima is something more weird, like we'll see examples. So this calculation is the easiest one, this eta 1, eta 2 calculation. But the important thing to remember is it doesn't really show the exact features of Goldstone's theorem that you might have expected. But you say, okay, that's because we chose some simple coordinates. You see, Cartesian coordinates are in some sense simpler than polar coordinates, because polar coordinates have this funny behavior at the origin, and in some sense the direction of theta is always changing. So it's not as simple, subtle, more subtle. But it's the right one to see the real power of Goldstone's theorem. Okay, so more questions?
So just to
Yes.
clarify the discussion, so when we took r and theta,
Hmm.
we saw that the theta field is massless and
Yeah.
there is some derivative coupling.
Yes.
And here we are seeing that this eta 2 field is massless and there's some other interaction.
Yes. Yes.
That is
That's right.
we-
And there's a potential.
And we identify these massless fields with the Goldstone.
Yes. Yes. Okay. Now all this, one thing I should emphasize, none of these things is true for the real scalar field where there is no continuous symmetry. So it's very important to realize that Goldstone's theorem only applies to continuous symmetries. So in the real phi case, there were two minima, not a continuous family. Because there are two, there's no mode which can smoothly run around, because there's nowhere to run. It has to either be here or jump to there. It can't run around. When there's a continuous space of minima, it can run around. Now there's a formalism which I'm not going to develop for the most general, how to study the most general examples, but I'm going to give you two illustrative examples for the simple reason that this example is U1, which is abelian, but we have learned from the beginning of this course that there are things called non-abelian symmetries, namely ON and UN, for purposes of this course at least. And it would be good to see how spontaneous symmetry breaking works for theories which have ON or UN symmetry. And luckily, those theories you already know. We just have to write the correct Lagrangian for them. So let me start with the ON vector model, which we introduced long ago. And it's Lagrangian. So it has a bunch of fields phi I, which are real. And now I simply take lambda by 4 phi I. As my potential. And right away, I have a spontaneously broken symmetry, ON symmetry, because the vacua are defined by phi I equals A squared. Now, what is this space? It's a hypersphere, and I goes from 1 to n. So imagine an n-dimensional space where n can be anything, however large we like. In it, we put a kind of a sphere of radius a. Okay, so the dimension of the sphere itself is n minus 1, right? Okay, so this is an n minus 1 dimensional sphere. And in fact, if n is 2, then this is a one-dimensional sphere, that's a circle, and it's actually the same as that model, because that's U1 model, and U1 is the same as O2, apart from a discrete transformation. U1 is the same as SO2, so the n equals 2 special case of this is a model we already did. Except here I've presented it in real variables, so in fact these are already the phi 1 and phi 2 of that model. Okay, but now I'm generalizing it to arbitrary n. Very good. So this is an n minus 1 dimensional sphere. Now notice that this equation is preserved by On acting on the phi. And now let's do a count of how many symmetries are broken and how many are preserved. Okay. So that's fine that the equation is preserved by On. That's the statement, sorry, I shouldn't have even written that. That's the statement that the Lagrangian is preserved by On. But now we need to expand around a vacuum. So what vacuum should I pick? Phi I is an n component vector. So the most general vacuum I could pick is something like A1, A2, A3 up to An, such that the sum of squares of all of them is A squared. That's all the requirement. But as you probably realize, by suitably rotating my axis, I can put the component all into I can put the entries all into one component. So I have 0, 0, dot, 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 0, and in the last place I put A. This works fine. Okay, so this satisfies that. And now I would expand phi I. So this is phi I classical. And I would expand phi I as this thing plus eta I. So which means phi I is actually eta 1 up to eta n minus 1 and a plus eta. A plus eta n. Good. Now the question is, how many symmetries did we break in this process by choosing this vacuum? How many of the so first of all, how many were there? This is On model. So it has n, the dimension of On is n minus 1 over 2 continuous symmetries. That's the dimension of the space. How many of them does this choice break? How do we calculate that?
So isn't it similar to how we found the symmetry of the circle in the...
Well, in the case of the circle, by picking one point, it broke all the... There was only a U1 symmetry, one continuous symmetry, and by picking that point, we broke it.
No, I mean when we had that model wherein we had the constraint phi.
Yeah. It's exactly that. That's right. In
So
fact, this is...
isometries of the sphere
In fact, isometries of the... So, but let's be a little more precise. So, the question is, how many symmetries did we break? So, do you have a number based on what you said just now?
So for isometry, so there will be SOM for the sphere. So that minus this.
Good. So the correct way to do it is ask how many symmetries are preserved by this choice of vacuum. Okay. Then I'll subtract that from how many symmetries I started with, and whatever is the difference is the symmetries I broke. Is that clear? Okay. So how many symmetries are preserved by, so which matrices which are in On preserve such a vector?
SOM minus 1, right?
So On minus 1. So the vacuum is preserved by On minus 1. What does that do? That's a orthogonal rotation of the first n fields with no rotation on the last one. It's similar to the question that if I have in 3 dimensions the vector 0, 0, 1, then which rotations preserve that? They are the xy rotations, because they rotate x and y, but they don't rotate z. Since I put some number in the third place, that will be fixed. It's the same thing here. Okay, so therefore this broken symmetries, and this On minus 1 has dimension n minus 1, n minus 2 over 2. So therefore broken symmetries are in number the original symmetries n minus 1 over 2 minus the ones that the vacuum preserves. Because if the vacuum doesn't preserve, then it's broken. And this is what Goldstone theorem says will be the number of massless or Goldstone fields I should find. And when I do this calculation, I find actually n minus 1. So there should be n minus 1 Goldstone bosons. should be okay. Now there must be n minus 1 out of these n fields eta 1 up to eta n, because that's the total number of fields. So n minus 1 of them should be Goldstone bosons. Which ones must they be? Obviously the first, n minus 1, because these are all symmetric. This is singled out to have a vacuum expectation value and be shifted by that, while these are all completely symmetric. So it makes sense that eta 1 to eta n minus 1 should be the Goldstone bosons. And we can verify that very easily by expanding, take this Lagrangian and plug in this expansion and calculate. Okay, and when you do that, you find a straightforward answer.
Sir,
Yes.
I did not understand how do you say ki, the number of broken symmetries equals to the number of Goldstone bosons?
That's what Goldstone's theorem says. Goldstone's theorem says for every spontaneously broken symmetry, there is a massless boson. That's the theorem. In the previous example, there was one there was one symmetry to start with, U1. It was spontaneously broken, and there was one massless boson, either theta or eta 2, depending which frame we work in. And now I'm going to the general theorem, which says that for every spontaneously broken symmetry, there is one massless boson. So every time, if there are many symmetries that are all broken, then there must be that many Goldstone bosons. That's the theorem, yes.
We like here you did not derive the theorem, right? Like
No, I'm just going to show that I haven't yet derived the theorem at all. So I thought about it. The derivation is not very difficult, and it's there in Peskin and Schroeder's book. If you're interested, I encourage you to look it up. I thought it's more practical to go through a few examples and see that it works out in those examples. And also, because I've given you the physical picture, in some sense we do understand what's going on. It's just the statement that when a symmetry is spontaneously broken, then that symmetry is realized in a space of minima rather than a single minimum, and it's the rolling on that space which is the Goldstone boson. And if there are n minus 1 broken symmetries, then I have an n minus 1 dimensional space of minima, and that's the analog of my circle of minima, and then there must be that many Goldstone bosons.
so for example, if we had expanded this in R and n minus 1 theta.
Yes, we could have expanded it in R and n minus 1 thetas. That's where it starts to get a little complicated, and I'll also tell you why. Maybe I'll tell you right now. You may wonder, how was I guaranteed that the difference between this and this would come out to be a number which is at least less than the total number of fields I have? It's strange, right? This number is bigger than n, this number is bigger than n, but their difference is less than the number of fields I have. So I'll write a statement, but I don't expect everyone to understand it or even use it. But the statement is the following: the manifold of broken symmetry is the coset space On upon On minus 1. To understand this statement, you need to realize that a Lie group itself is a manifold of dimension of the group. So the group dimension of On is that. So On is a n minus 1 over 2 dimensional manifold with a certain geometry. On minus 1 is the same thing except for n minus 1. And whenever I have a group that is a proper subgroup of this, under the right conditions, I can take the quotient of one group by another, and that's called the coset space. And the coset space is a symmetric space where the denominator symmetries act linearly and the numerator symmetries which are not in the denominator act non-linearly. So this is the full story, but as I said, it is a little bit beyond the mathematical level I want to assume for this course. If I could formalize this, which most textbooks don't, QFT textbooks don't do, but specialized references will do. then I would have to look for coordinates on the coset space, and those would be your n minus 1 thetas. You just mentioned 1 r and n minus 1 thetas. So the n minus 1 are going to be coordinates on the coset space. And so I need to find a way to parameterize coordinates on a coset space. Luckily, when n is 2, then O2 is a simple space, namely a circle, and O1 is nothing at all. So the coset space is the circle again. So it was a very simple case. But in general, it's more complicated. That's why the r theta parameterization is not so easy to do. But it's known, it's done, it's actually even used in physics. It's just going to take me in a direction which, to explain properly, I would have to go through the mathematics of group manifolds and coset spaces, which I don't want to do. Instead of that, we can do the naive thing. We simply plug in this form of phi I, expanded like this, and write the Lagrangian and verify whatever we expect to be true. And when we do that, we find, so what I'll do actually is to call, I'll give this a different name. I'll call this sigma. And these, eta 1 up to eta n minus 1, I'll call eta a, where a goes from 1 to n minus 1. And now I find the Lagrangian. L is half del mu eta a, del mu eta a. Everything is real in this problem, by the way, because we started with an ON model where the fields were real, etas are similarly real. Then I get a kinetic term, del mu sigma. Del mu sigma. So far, so good. Then I find a mass term, which is quite familiar, minus lambda a squared, sigma squared. And then I find a cubic term, minus lambda a sigma, sigma squared plus eta a, eta a. And then I find quartic terms, which I'm not going to write. I think you'll find this model worked out in Peskin and Schroeder's book. Okay, so does this conform to what we were expecting? Well, as you can see, the only field with a mass is sigma. This is the mass term for the sigma field, and no other field has a mass. There's simply no quadratic term for any of the etas. But there is a cubic term, eta, eta, sigma. And there are quadratic terms involved, quartic terms involving etas and sigmas. And why are we not worried about that? For the same reason as before. Namely, these are Cartesian coordinates. In an n-dimensional space, we just took Cartesian coordinates of the field. And so the field is really tangent to the space of minima only at the point which I chose, which is 0, 0, 0, 0, dot, dot, a. And so only the quadratic term vanishes, but these terms are there. If I was smart enough to parameterize it in terms of the coset space, and I'll show you one more example where it's easy to do. Basically, it's always easy to do when the denominator is trivial, because then the coset space is the group itself, and group we know how to parameterize using the exponential of the generators. It's a problem when the denominator is non-trivial. Okay, so yeah, so to summarize, etas are Goldstone bosons, but in this parameterization, they do have a potential. Okay, and if I did a better parameterization, I would find n minus 1 theta fields, which really run along this n minus 1 sphere, and they therefore don't have any potential. Good. And one more thing we can comment while inspecting this. The ON minus 1 symmetry is obvious. If somebody gives you this Lagrangian, and even the quartic term has that feature, well, this is an obvious ON minus 1 invariant. So is this. So it's obvious that there's ON minus 1 symmetry. It's not at all obvious that there's ON symmetry, because that would mix sigma with eta. Now this is a nice one. This bracket is ON invariant because sigma squared conveniently came with that, but sigma is also sitting here. Sigma is also sitting here. So any linear action of sigma mixing it with the eta cannot keep this Lagrangian invariant, and yet secretly it is invariant because it was invariant to start with, and we never broke the symmetry. So the spontaneously broken part is hidden, and that's the that's the sort of picture. So,
So,
yeah, yes.
are those symmetries similarly non-linear like the non-linear?
Yes,
sigma?
absolutely. And actually, this this model is called the linear sigma model. I should have said. The non-linear sigma model simply comes by saying, so right now what we did was look at the space of minima. But supposing we said that the field is forced into its space of minima only, it doesn't fluctuate out of that space. Okay, then I can eliminate sigma in terms of all the other fields, solving the constraint, and I get the non-linear sigma model, which manifestly embodies this coset space structure. Non-linear sigma model is written on a coset space, and it has the symmetries of the denominator as its linear symmetries and the remaining symmetries as its non-linear symmetries. So these are called non-linear Lagrangians or non-linear sigma model for that reason. And well, just to mention, now I didn't really prepare to talk about it, but I'll just mention that should I mention or should I not? Some part of me says I should. So this is related to pions. Let's see, maybe next time I'll talk about pions. I don't want to get it wrong. Okay.
Sir,
Yes.
sir, actually in classical model you said that there are two minimas which are discrete, so small
In the real case.
in the real
Yes.
case.
Yes.
So,
Yes. Yes.
So small fluctuations will
Yeah.
not lead us to the other
Yeah. Yeah.
similarity, but in continuous case,
Yeah, in the continuous case, the point is that small fluctuations do lead us from one to the other precisely because of the presence of the Goldstone boson. That is the fluctuation. If you see, it's a field with no potential. So if I put it in one point in the space of minima and give it a tiny kick, it's going to keep traveling and keep going around the whole space of minima. That is the mode. So it's different, and this is why Goldstone's theorem applies. In the discrete case, we just have two minima and it's over. In the continuous case, Goldstone's theorem applies. However, there's yet another case, which is the discrete case or the continuous case in two-dimensional field theory, where something really different happens, which is the Mermin-Wagner theorem. Maybe at some point I'll talk about that. My main purpose in this course was to do 4D, 3 plus 1D field theory. But it's really good to know that theorem. So but it's a little tough. So I'll try to explain it another time, if I get a chance. Good. So let's do one more model and then stop. So the one more model is I'm going to consider an SUN vector model, and for that I just put a few stars here and there and change the normalization, and that's my model. And it has n squared minus 1 symmetries. Okay, so now it's actually this model has UN symmetry, but UN is U1 times SUN, and I won't worry about the U1 because that's not going to be important.
UN also, right?
This model might have, yeah, so this model probably has O2N. You're quite right. That's true, but so what I'll assume is that maybe it has some more interactions which only are preserved by SU2, not even U2 and not the remaining ones in O2N. So that from that point of view, I'll call this the SUN vector model. And now what's the discussion? Well, as usual, I need to find phi I classical, but now a little bit of a trick. So it's 0, 0. Again, I'll put A in the last place, but I can put, so A is a real number. I could in principle have put any phase times A, that would have worked also because phi is complex, but I'll just put A. Okay. So now the question is what does this break? What are the preserved symmetries? So now you can see clearly the steps, right? We ask what are the preserved symmetries preserved by this vacuum, and they are SUN on this part. So SUN minus 1 acting on the first n minus 1 components. So the broken symmetries are so actually the coset space is SUN over SUN minus 1, which is also a valid coset space, but if you are just counting numbers, then n squared minus 1 minus n minus 1 square minus 1. The dimension of SUN minus the dimension of SUN minus 1. And what do we get when we do that? We get 2n minus 1. And is this good or bad?
Two n for the each separate component.
Each real.
Exactly. So there are all these. So this has a bunch of 2n. So this is complex. Therefore, there are two components in each place, real or imaginary. So 2n minus 2 among these. Then here I'll have one which is unshifted and one which is shifted. So in my conventions, the real part of this one is shifted by A, the imaginary part is not. So in other words, I'm writing that phi is equal to eta 1 up to eta 1 up to eta n minus 1. And in the last place, A plus eta A plus, if you like, sigma, no, A plus sigma plus I eta n. Yeah, this is also not good. I need some notation which will be good for 2n minus 1 fields. Anyway, it's what I just said. So let's write this as A plus sigma 1 plus I sigma 2. These are not Pauli matrices, this is just the sigma field. Okay, so etas are all complex, 2 sigmas are real. So total 2n fields. Now sigma 1 is going to be massive. It's the one which got shifted. In our experience, the one that got shifted turns into the massive one. While 2n minus 2 of these plus that one together form 2n minus 1 that are going to be Goldstone bosons. That's the prediction. Okay. So now again, it's up to us to work it out. But there's one case which is not so hard, which is SU2. So it has 3 symmetries. And in that case, one possible, so now I expect 3 Goldstone bosons. N is 2, so 3 Goldstone bosons. And a convenient way, so here I could have parameterized it as eta 1 plus I psi 1 and A plus eta 2 plus I. So yeah, I really am running out of notation. Eta 1 plus I eta 2, A plus sigma plus I eta 3. How about this? So eta 1, eta 2 and eta 3 would be the Goldstone bosons. Yeah, there's a question. Okay, so it's n is 2 now. I'm doing SU2. So there are 2 components. Both are complex, but the second one has to be shifted by my vacuum expectation value. So it's A plus sigma. So sigma is the real part of whatever field was here. So it knows that it has been shifted. While eta 3 is the imaginary part, it hasn't been shifted, nor have these. So then eta 1, eta 2 and eta 3 are going to be the Goldstone bosons, and you can easily insert this expansion into this and verify that for yourself. I think by now everybody can do that, right? That's a very straightforward exercise. Good. But there's something better we can do, which is to notice that in this case the unbroken symmetry is SUN minus 1, which is SU1, which is trivial. So when the unbroken symmetry is trivial, it means that this eta 1, eta 2 and eta 3 are moving on the space of SU2 itself. The whole SU2 is broken. Okay. So in general, we say words like, in the ON model, we would have said ON broken to ON minus 1, or we say SUN broken to SUN minus 1. And the Goldstone bosons are valued on the coset of this by that. But in the special case here n equals 2, O2 is broken to nothing because O1 is nothing. And so in that case, the Goldstone boson is nothing but valued on the circle. So it's a coordinate of the circle. That's why it was theta. In this case, SU2 breaks to nothing. So therefore, the Goldstone bosons are valued on the manifold of SU2. but you know that the manifold of SU2 is the three-dimensional sphere. So that's it. So actually I can parameterize, so that now I can find the useful parameterization which exhibits the Goldstone boson, which is to write phi of x, this phi I, the original field with I going from 1 to 2, as e to the I eta a t a 0 a plus sigma of x. So my fields are eta a of x, I shouldn't call them, theta, I'll call these theta, and sigma. What have I done? Well, this is a general element of SU2. I think this you know. TA are the generators of SU2. So theta A TA is an element of the algebra. If I exponentiate I times that, I get an element of the group. So this is an SU2 element. Okay, so I can parameterize my field as a SU2 element. This is a matrix Ij acting on this vector J. So two component vector. This is a 2 by 2 matrix and this is a 2 component vector. So summed over J is, this gives me phi. This is a parameterization. And in this parameterization, you'll find that sigma is a massive field as usual, and all the three thetas are completely potential-less. So these are actually the correct coordinates on that space of minima. So this is an exercise, which I've also put in the notes. So now, of course, you can do, this is binomial, doesn't exhaust by any means the set of spontaneously broken models I can make, because I could take multiple scalar fields in different representations of the group, SUN or ON or whatever. I could use the adjoint, which I haven't used yet, and which is little bit, has its own intriguing features. We studied matrix models in the early part of this course. So I can have a matrix model where I take trace of phi squared minus a squared, where phi is a matrix, and I have a spontaneously broken theory. But now how the exact symmetry exactly breaks and all is more complicated. Then I can have multiple fields like phi, chi, psi, and I can couple them all to each other. Some can be doublet of SU2, some can be triplet, and so on. By the way, this example is actually realized in the standard model, which does have an SU2 Yang-Mills symmetry in it. And so you may wonder what in nature are these three Goldstone bosons theta A, and that question I'll answer tomorrow when I talk of the Higgs mechanism. So that's why this example of SU2 breaking to nothing is useful. It's not exactly like that, because in the standard model, SU2 cross U1 breaks to U1. And the U1 to which it breaks is not the original U1, nor is it a subgroup of SU2. It's a subgroup of both together. That's a little twist. I think Arun will show you all that if you're taking his course. But I'll also try to show it to you. Anyway, so just to emphasize that this whole thing of what could be the space of minima of a scalar field theory can be an enormously complicated question requiring a good understanding of coset spaces. But the general rule is always the same. Start with some symmetry, choose a vacuum which breaks it to some space of some smaller symmetry, and then the difference between the symmetries you had and the ones that are there in the vacuum is the number of broken symmetries, and that's the number of Goldstone bosons. And not just the number, the more powerful statement is that these cosets are actually the space of Goldstone bosons. That space is interesting. The dimension of that space is the number. Most, again, textbooks only tell you how to count the number, as I showed you. But the fact that there's a geometrical space in which these Goldstone bosons really live, that's a nice thing. So I'll stop here.